Sometimes people show the execution of interrupts or programs considering the interrupts in this way. They say, imagine a program is getting executed and an interrupt happens. So the return address here would be pushed onto the stack, meaning that if we are at this instruction, we know at the execution of this instruction, the PC is actually pointing to the next instruction. So we know this is called the return address because after the interrupt, we want the CPU to return to this exact position. So we say the return address would be pushed onto the stack, the PC would be loaded with a new value, and the CPU would jump to the execution of another program, which we call it the ISR of the new program, new interrupt, sorry. So this ISR or this program would get executed, another interrupt might happen. Therefore, the same thing would happen. PC would be pushed onto the stack and would be loaded with the address of the new ISR or with the starting address of the new ISR. The new program would get executed. At some point, another interrupt would happen. At some point, again, another interrupt would happen. At some point, another interrupt would happen. Now, this program would get executed without any other program or without being interrupted by any other program. So after the execution is completed, the top of the stack would be popped out into the PC register. This would be the return address of previous program. So the CPU would jump back to this program. This program would get executed, would be completed. It would, again, the top of the stack would be popped out into the PC. The top of the stack would be the return address of the previous program. Now, as this program is getting executed, another interrupt might happen. Therefore, the return address here would be pushed onto the stack. PC would be loaded with the new program or the ISR of the new interrupt. Then the program would get executed. Anything is at the top of the stack would be popped out back into the PC. Therefore, the program that was interrupted would get resumed, would be completed, would go back to the program that was interrupted because of this interrupt. This would get executed, would go back, this would get executed, would go back, meaning that the top of the stack would be popped out back into the PC, and finally the first program would be completed again. Now, we talked about a set of instructions which start with RST, and we said if we mean RST0, it is an opcode that the programmer writes 11000111 in a location in memory, and he has written, for example, his ISR or the ISR that a program that he has in his mind, and then when he writes RST in any position in the memory, when the opcode of the RST0 is fetched inside the IR register, the CPU would look at this opcode, would understand that it should multiply 000 means 0. It would multiply this 0 by 8, which means it is 0. So it means a call to the 0 position. Therefore, PC would be loaded with 0 and it would start executing programs as 0. Now, at 0, the programmer might have written a jump instruction to an address called like F000, which the CPU would again jump to this location. Or another example, RST7 means FF in hex. If this value is brought inside the IR, what the CPU would do is that it says 7 times 8 is equal to 56. 56 is 38 in hex, which means that the CPU would push whatever value is in the PC register onto the stack and would jump to this location, which we said this is equal to call 38 as well. And we know that call is push whatever is inside the PC and then jump to 38. Again, 38 in hex is 0011 1000. Now, we call, or these interrupts are called software interrupts. On opposite of hardware interrupts, these 5 are called hardware interrupts. Trap is sometimes called RST 4.5, RST 7.5, 6.5, 5.5, and INTR. On the first glance, You might say, well, you already explained that RST anything means a call to that argument times 8, that the value in the PC would be pushed onto the stack and the PC would be loaded by that argument times 8. So maybe this RST 4.5 means 4.5 times 8 would be 8. Well, 8 times 5 is 40, 8 times 4 is 32, plus 4 is 36 in decimal. 36 in decimal is equivalent to 24 in hex. So maybe RST 4.5 means call to 24 in hex or call to 36 in decimal. And if we have 5.5, maybe this means call 00 to C, because 5.5 times 8 is 44 in hex in decimal, and 44 divided by 16 is 2C. So we know addresses are actually 16 bits long. If you have 2C, it means 002C, as 24 means 0024 in hex. So maybe RST 5.5 means call 002C, or RST 6.5 means call 0034. If you multiply this by 8, you'd get the same result. Or maybe RST 7.5 again means call 7.5 multiplied by 8 would be 003C. And you are actually right. But what you are wrong about is that it is not completely RST. These RSTs, every one of them would have an opcode, while these RSTs here, they don't have any opcode. So if they don't have any opcode, how does the CPU understand that where it should jump to, or how will the programmer write his program? That how the programmer would say, for example, I want the RST 7.5 to get executed. He could say, I want the RST 4 to get executed by saying 111001111, which is the opcode for this one. If he writes this in the memory, then a call to 32 would happen, therefore, or 20 in hex, therefore, well, a simple call would happen. But the programmer cannot do this if he doesn't have an opcode. So how would he write the program? Well, he can't. He can't write the program of RST 5.5 because, or any one of these, because they are called hardware interrupts, meaning they are actually the names of some pins. This is the 8085 pin diagram. And if we look, the pin number 6, 7, 8, 9, and 10 are called trap or RST 4.5, RST 7.5, 6.5, 5.5, and INTR. So if these pins, as you see, they are hardware, part of the 8085 microprocessor. A device would be connected to these different pins. Now imagine one of the devices which is connected to the trap would send a signal here. This is, all of these 5 pins are input pins. So the CPU would check this interrupt. If these pins, the signal coming here, goes high or stays high, then the CPU would execute something which is equivalent to call 0024. You see, there isn't any opcode. The IR register wouldn't have anything. These are hard coded in the CPU, that whenever CPU sees the signal coming to the trap going high or being high, what it does is that it would push the value currently inside the PC onto the stack and would load the PC with the value of 2024. Therefore, from the programmer's perspective, what you are seeing is that the CPU has been interrupted by another device, maybe the keyboard or the mouse, and another program is getting executed, or the ISR that of a device of an interrupt has been executed, and then after the execution has been completed, then the top of the stack would be popped back, and then the program that was interrupted by the device connected to the trap would be resumed. Now, the same thing applies about others. RST 7.5, if the CPU sees the signal coming to this pin goes high, not staying high, but goes high, then it would push whatever is inside the PC on the stack, and then it would jump to the location of 003C. Why 003C? Because we said this would be multiplied by 8. But you see, the difference is that here the CPU would understand by looking at the argument that you have written as the opcode in the IR, but here the naming is that you understand that RST 7.5 is 7.5 times 8, the address that CPU would jump to. These are hard-coded inside the CPU. Now you might say these are also hard-coded as a part of the control unit, but you have control over these. You write their opcode inside the IR, while these are just pins. So next pin is RST 6.5, meaning that when pin number 8, you see, when pin number 8 is high, not going high, when it's high, then the CPU would jump, would again push anything in the PC on the top of the stack, then would jump to the location to C. And RST 5.5, yes, this is actually 002C. This would be 34. Let me make sure of that. 6.5 multiplied by 8. 8 times 5, we would have 4. 8 times 6. And this would be 52. 52 divided by 16 would be 634. So 0034 would be the location that the CPU jumped to if this pin goes high. Also, RST 5.5 would jump to the well, obviously would jump to the location of 002C. But what about INTR? When INTR gets a high voltage or high signal, the CPU wouldn't understand where it should jump. So it would send a 0 on the INTA, or interrupt acknowledge, sometimes we call it, asking the device or any interface between that device and itself to give me the address. We call these addresses vector address, to give me the address that you want me to jump to. Now, we could categorize all of these 5 interrupts, even though there are 6 pins related to interrupts out of the 40 different pins in 8085. 6 pins are related to the interrupts. Trap 7.5, 6.5, 5.5, and INTR are for receiving the interrupts. INTA is actually working alongside INTR to receive the vector address, because INTR vector address is not hard-coded inside the CPU, while all the addresses of 24, 28, 2C, and 3C are hard-coded as part of the CPU. Now, we could categorize all these 5 interrupts in this way. We say interrupt trap 7.5, 6.5, and 5.5, they are vectored interrupts, meaning whenever those pins get activated, they would jump to this address after pushing the PC on the top of the stack. But as we said, INTR doesn't do that because it works alongside the INTA. We call trap edge triggered and level triggered, meaning that the CPU would look at the trap pin. What was the trap pin number? Would look at the 6 pin, pin number 6. If it sees that this pin goes high or stays high, going high means it is edge triggered, that the CPU activates the interrupt or would jump to the location of T2024 if it goes too high. Level triggered means it would activate it if it is high, that pin. Trapped is an interrupt that works with both of them. You can't ever disable the trapped interrupt, and trap has the highest priority. Now let me explain others and I tell you. RST 7.5 is also edge triggered, meaning it should go high. The CPU, what CPU cares about is going high of this pin. RST 6.5, 5.5, and INTR, they are level triggered, meaning that going high is not important for the CPU, but being high is important for them. About the priority, the trap has the highest priority, meaning if trap just has gone high, the pin RST 7.5 has gone high, or I should tell you in this way. If this pin gone high, pin number 7 has gone high, 8 is already high, 9 is already high, and 10 is already high, what the CPU would do is that first it would execute the ISR related to the trap. After it has been completed, then it would move to the ISR or 7.5, meaning it would jump to this location. Then it would jump to this, then this, and then the last one, and finally it would go back to the program that it was interrupted the first time. Then we have these two columns that I want to explain to you in this way. Trapped can never be disabled, meaning any device that you connect to this one, anytime that this pin goes to high or is high, the CPU would jump to the location of 0024 no matter what. But others you could disable. There are two instructions in the CPU, in the AT85 CPU. Out of the 246 instructions that we've been talking about, there are two instructions called DI and EI, which they actually have some, let me just write down their opcode first. The opcode of DI is equal to F3, which is 11110011. If this value is inside the IR, what the CPU would do is it would disable all the interrupts. All the interrupts, I mean 7.5, 6.5, 5.5, and INTR. It means that it doesn't matter what happens at this pin, these pins, the CPU would ignore them. You can't disable trap, only these four. EI, or the opcode of FB, which is 11111011. If this opcode is in the IR, on the contrary, the CPU would enable all the interrupts. Again, trap is always enabled. But sometimes imagine that as this AT85 was being manufactured, the designers thought, well, what if someone wants to enable some of them, like he doesn't want to disable all of them, want to maybe disable some of them. So two other instructions they created for AT85 as part of these 246. They were called SIM and RIM. What this means is that SIM it means that you could mask RST 7.5, 6.5, or you could, let me say it this way, you could disable RST 7.5, 6.5, 5.5. All of them together, one by one, or anything that you want. As an example, let's say you want to disable these two interrupts. So you could say EI, you don't say DI to disable all of them. You say EI, and then using SIM, which we later talk about its format, to mask these two interrupts. It means that if at the pins of 6.5, pin number 8 and 9, whatever happens, the CPU would ignore them, but other interrupts would get attention of the CPU. So when we say maskable by SIM, means that trapped and INTR, you can disable or mask them using the SIM. RIM tells you what interrupt has been masked. So you do the masking using SIM, you do the disabling using SIM, and using RIM, you understand if they were actually masked or not, or which interrupts are currently masked or not. So DI effect means, as we said, being disabled. All of them could be disabled other than trap. Trap cannot be affected by any one of them. So these were a summary about all the interrupts, but the way that I want to categorize them is in this way. As I said earlier, I like to think that, actually not liking to think, but interrupts are calling instructions, whether you like it or not. And they are alongside the return. Using call, you push the return address, you jump to a specific location. After interrupt is getting executed, you return to the program that was interrupted by the interrupting program. Now, a better way to categorize them, at least for me, is to say this, that call instructions, these 9 call instructions, are non-vector interrupts, meaning that the address that the CPU would jump to is not implied, is fed by the programmer. They all have an opcode. All of these non-vector interrupts, they would have an opcode and the address that is fed to the CPU by the programmer. And then you say vector interrupts, meaning the opcode itself. You see, I'm talking about only the opcode. I know in the instruction that the programmer writes in the memory, the vector is actually as the 2 bytes after the opcode in the call instruction. In the opcode of the RST, the instruction is one byte, as the opcode is 1 byte. The address is implied inside the instruction. So we call them vector interrupts. And then you have the hardware interrupts, which again, this last one is non-vector, and all these 4 are vector addresses. And all of these has been explained. But as I said, in the books, in all the exams, they show them in this way. They don't say call or interrupts. They say we have software interrupts and we have hardware interrupts. Software interrupts, it means we have opcode. The software interrupts are 1 byte instructions. That 1 byte tells the CPU the address that it should call to, or it should jump to that location. And also software interrupts, it doesn't have any meaning. We have an opcode for software interrupts, as it is the manipulation of different pins of going low and high. If they tell you that are software interrupts maskable, you should laugh, because what do you mean maskable? Well, software interrupts are opcodes, or what the programmer could write or not. Well, if you want, the programmer wants, he could write CF as an instruction or not write it. What do you mean by masking? Well, he could just, if he doesn't want the RST1 to get executed, obviously he wouldn't write this instruction. Why would he write an instruction that he doesn't want to get executed? But hardware interrupts, could they be masked? Well, yes, because it's not in the power of a programmer. It's a pin, and the device is connected to the pin. A button might be pushed on the keyboard, a mouse, or anything else. You might not want the program that is getting executed to be interrupted by any device which is connected to any one of these pins. So it makes complete sense to mask one of the hardware interrupts. Again, based on the exams, as you see, we have 8 software interrupts and 5 hardware interrupts. These are not the calls. They are not usually categorized as the interrupts. But you know, at the end of the day, or intuitively, all the interrupts are some call instructions. So this was about it. Maybe in the next lecture, I talk about the architecture of the interrupts, that how interrupts are actually implemented in hardware inside the CPU to maybe give you a better intuition. See you in the next lecture.